This is our Trebuchet Project. Our group consisted of Kyle Nalley, Kent Whitlock, Nathan Ferry, and Noah Wilson. The engineering challenge was to design a trebuchet that could fit within a 1x1 box or be assembled out of a 1x1 box in less than 2 minutes to throw an approximately 20-gram marble, and at least 25% of the trebuchet had to be made using either the 3D printer, the wood cutter, or the laser cutter. We opted to use the laser cutter.
We didn't have many different designs that we thought of, but a couple. The PCP pipe look and all wood trebuchet. We decided to go with the PCP pipe design because it would be easier to assemble, deassemble, and easy to work with. The design offered easy ways to manipulate and change the structure of the trebuchet very easily, without changing the design. The most critical aspect of the design was probably the way the wood arms sat in the tubes of the PCP pipe. The manufacturing part was easy because, like I said before, manipulating the PCP pipe was very easy to do, and there were many ways we could do this, including the way the arms and elbows could put on. Cutting the PCP pipe would be very easy. Our original design consisted of 16.825 inches long arm. This would fit perfectly within the 1 foot box diagonally across. The arm consisted of 6 pieces of 1/8 inch thick wood, super glued together. We used an 8-inch bolt that was threaded to put through the arm inside the tubes, which offered as the bar to fling the marble. In this, we changed 2 aspects of the design. We changed the vertical leg of the structure from 6.89 inches to 12 inches, the same height as the highest we could go. From there, we changed the small legs of the bottom from being 1 inch off the 12 inches to right in the middle at 6 inches to offer more stability and support.
Construction of the pivot and arm. At first our plan was to build a trebuchet that fit in the 1x1x1 without any assembly, making our total height about 12 inches and our pivot about 9 inches. But we decided to maximize the height of the pivot, but in doing this we needed to find a way to make the arm detachable. We changed the pivot to be about 11.25 inches tall, and found a very easy solution to make the arm detachable. Originally, we designed the arm to be drilled into the side of the PVC, but we discovered a much easier and efficient way by just placing 2 90-degree connecting tubes on top of the PVC pivots, and using that as the housing for the arm's bolt. This made the assembly process take less than 10 seconds, as all we had to do was twist the PVC so that it could fit the bolt and the arm, both connecting tubes. We also made a change to the pivot to be in the center of the trebuchet, as the masthead should be put somewhere else, but we believed it would have tipped over after each throw. So we decided to change the design and place the vertical pivots to the direct middle of the trebuchet, providing a lot more stability. We spent a lot of time researching things we could use for a counterweight. We wanted our ideal mass to be about 5.1 pounds, but we couldn't really find anything small and easy to put together, and cheap. I asked my dad for some help in figuring out a solution to our problem, and he found a small cylinder that was about 3.5 pounds and welded 2 nuts to the end of it. This weight ended up being 1,525 grams, and this was about 2/3 of the weight we originally wanted. We decided to just go with it and see what happens because we could add more weight on with duct tape. After the first day of testing, we decided to use the second day to test our trebuchet by adding 2 more pounds to the counterweight, with a total of 2,538 pounds. The final counterweight consisted of the red cylinder with a pin with many washers duct taped to the bottom. The pouch design ended up being very important as it had to hold the projectile properly and launch it without releasing too soon or too late. The pouch was made of fabric and cut out of a diamond shape. Then it was folded in half, forming a triangle. Then the 2 base corners of the triangle were stapled to form the pouch. Then we cut 2 small holes in the top flaps of the pouch and fed several loops of fishing wire through to ensure it wouldn't break mid-throw. As you can see in the pictures below, this is what our pouch design was based off of. Also, no exact measurements were used in the construction of the pouch, as it was supposed to be a test pouch to see if it worked. Finally, the release mechanism. For the release mechanism, we had no intention of making one in our original design, but when we constructed an idea for the second time, the process was extremely simple. We knew we had to have one because the projectile would get caught up if the upper string was attached to the arm permanently, like the bottom one. So we hot glued a used axle rod from a past project to the top of the back side of the arm. We then made a loop in the fishing wire and looped it onto the rod. Tension on the top wire, it would stay on the rod, and when the arm swung upwards near the top of the extension, the top string would release from the rod, allowing the projectile to fly at a near perfect angle of launch.
The performance of our trebuchet was phenomenal. There were no issues with the release mechanism or movement of our trebuchet, and everything went as expected. However, one problem that occurred was that the fishing line broke at the end of the first day of testing. We fixed this by simply replacing all of the current fishing wire that held up our counterweight with stronger, thicker fishing wire. The only other issue would be the difficulty of cutting the PVC pipe without pipe cutters. The smell was pretty bad. By using the mass of the marble, distance the marble traveled, mass of the counterweight, and the distance the counterweight dropped, we are able to calculate the efficiency of our trebuchet. As seen below, our actual trebuchet had an efficiency rating of 96.41%. This is a better rating than our original trebuchet, which had 87.52%. But how could this happen? When looking at the equations, almost all variables in the equation increase the efficiency of the simulated trebuchet. With a lower counterweight drop and lower counterweight mass in the denominator, as well as a higher marble mass in the numerator, this all benefited the simulated efficiency. However, our simulated trebuchet simply did not throw the marble as far as our actual trebuchet did, with a difference of 189 inches. This could be due to an underestimate of the simulation, as well as the wind helping the actual trebuchet, but only by a little, and is why our efficiency is lower. One change that we could make that would improve the performance of our trebuchet would be to fill the PVC pipe base with concrete. This would weigh down the trebuchet and cause it to move less during the release. We could have also tightened our pouch strings, which would only have gotten rid of the unused slack of the fishing wire that got tangled up. Another improvement would be to add a takeoff strip for the pouch, reducing friction between the pouch and turf, which would cause for a smoother release. And finally, getting rid of the threading on the bolt, which would also reduce friction between the bolt and PVC pipe, would cause for a smoother release as well.